Deutsch from the University of New Mexico. So Ivan got his PhD at Berkeley with Ray Chow, had a short stay in France, and then joined the laser cooling and trapping group at NIST in 1993. It's a hard time, long time ago. Ivan and I shared an office for 2 years at NIST. And the unusual thing was he was the theorist in an experimental group, and he survived our abuse. So we had a great time. We did some nice work on optical lattices and things. And then Ivan moved to the University of New Mexico as a faculty member, where he has been ever since. He's had a long career doing all kinds of things related to optical lattices, coherent control, quantum information, and the like. He started and is still the director of the Center for Quantum Information and Control, and is now the instigator of New Mexico's new big quantum push, the Quantum New Mexico Institute, QNMI, which is just getting formed and is in large part responsible to Ivan for its creation. And I guess it's an institution that's going to include UNM, Sandia, and Los Alamos. So I will say I've known Ivan for years, of course, and one of the special things about Ivan, as far as I'm concerned, is he's got fantastic intuition. So whenever I have a physics problem I don't understand, I can ask Ivan, and he can always explain it to me. So with that, I'll pass it to Ivan. You need to stick that on your sweat. Oh, and students working in 2170.
All right, very good. I hope the folks on Zoom can hear me. Thanks so much, Steve, for that very kind introduction. This is kind of like a homecoming for me. It's been a long while since I've been to the JQI, and seeing so many old friends and hopefully meet some new friends too. So thanks again for the invitation and the ability to talk to you about some work we've been doing on neutral atom quantum computing with nuclear spin qudits. So I'll tell you about that. As Steve mentioned, we've now established the new Quantum New Mexico Institute, and if there's one thing will help me my legacy, is our tagline: New Mexico is a quantum state. Yes. Now, people complain that we don't say New Mexico is the quantum state, but I'm a Bayesian, so I could say it's my quantum state, but it's not the quantum state, it's a quantum state. So one thing I just want to mention, I don't know if there are any undergraduates in the room. We're going to be establishing the JQI is our inspiration, and so we want to have similar kinds of programs. And there will be a graduate student fellowship program that's starting up for those who are thinking about applying for graduate school. So just wanted to mention that. All right, let's kick it off. So many years ago, I stole this slide from the internet. This was a slide from 2016. I think Franco Nori put it together at the time about the race to build a quantum computer and the various platforms that were being considered, whether it were superconducting systems, trapped ions, quantum dots, some crazy stuff like Majorana fermions, topological qubits, maybe NV centers and diamonds. Interesting list at the time. Interesting, right? No neutral atoms. Well, so I looked this up. I gave a talk like this last year, and I found the same. I texted. I was actually looking for the slide because I wasn't sure who made it when I stole it, and I came up with this. And so here we are. Interesting. So there's some newcomers in this. Photonics wasn't in the original one. And neutral atoms, which maybe this is somebody's vision of the race to building quantum. It's an interesting time. Having been someone who's been involved in this from the beginning, thinking about how optically trapped neutral atoms would form a scalable platform for neutral atom quantum computing. It's just so delightful to me to see what's happening in our field today. from the beginning, the question is why would we use individual atoms as the platform to build a quantum computer? And I would say, hands down, the world's most quantum coherent device is an atomic clock. Atomic clocks, the technology to design and build atomic clocks, is the foundation of the coherent control that everyone uses to manipulate quantum information. And well, it's dangerous with these numbers up here at NIST. I don't know if they're exactly accurate anymore when I get them. But the point really is that the ability to uh, uh, manipulate qubits, well, atoms are the best. And, in some sense, an atomic clock is a bunch of it is a bunch of non-interacting qubits. Uh, one tries very hard to keep those qubits from interacting with one another in an atomic clock, typically because the systematic shifts that would arise from collisions or other perturbations would ruin the clock. So the idea then of building a quantum computer on top of this platform is to go from, in some sense, being able to control a large ensemble of qubits or individual one-body systems to control of the many-body wave function, the many-body ensemble. And there's, as you know, been many important developments over the years, and I'll just highlight a few of them that have enabled us to do that. One is the ability to trap individual atoms and be able to address individual atoms and to be able to arrange individual atoms into whatever arrays that we choose to do. And there were many innovations that enabled that to the degree that one can now make defect arrays in 1D, in 2D, and of course, if you live in France, you have to make in 3D, you have to make the Eiffel Tower of atoms. And so that's one piece of this. And another very important piece is you now want to be able to not keep these atoms isolated from one another. You want to be able to control their interaction with one another on demand. You want to be able to turn those interactions on and turn those interactions off, whereby you can do this by exciting an atom to a very highly lying orbital, a so-called Rydberg state, where the electron's just waving out there in the wind, and one nearby atom will highly polarize it and enable us to make very strong interactions when the atoms are in these highly lying Rydberg states. These are very unusual states of an atom. The radius, the mean position of the electron relative to the nucleus is, some microns away, potentially. And at that scale, we have really extreme interactions, strong dipole-dipole or van der Waals-like interactions that are very strong functions of the principal quantum number. And importantly, the electron doesn't decay very quickly from that level. So there's enough time to be able to make the atoms interact, control that entangling interaction, and return the atom back to the ground state and be able to turn those interactions on and off. And the ability to do this well has taken some time. Developments in laser technology, making the right coherent lasers that can do this. But now the state of the art is kind of amazing. I mean, this slide is already, again, old in terms of, where things are at. But now one can achieve very high fidelity 2-qubit gates, getting up to hopefully 3 nines or more soon, the ability to do mid-circuit measurements, various tools that have been developed, trapping multiple species of atoms, being able to correct leakage into error conversion, programmable architectures with multiple zones to make logical qubits, etc. And very recently in the NDRES group was published this landmark paper whereby, every one of those little dots, there is one atom that's trapped in this big numerical aperture microscope where there's over 6,000 very, 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 very high quality qubits that are now trapped. And I'm sure soon we'll see a processor, a high quality processor on this. So there's been tremendous acceleration in the last few years, and it's been very exciting to see. And there's been lots of people, I'm not doing justice to the references on this, but just give you a flavor. Yeah.
Do you know what's the latest on kind of like sorting them?
In this guy, I haven't talked to Manuel. I have no clue. But I mean, last, the paper, as I think you know, was posted in the archive 9 months ago or something like that originally. So I can only imagine that they've done something with this since then, but I don't know what the state of the art is. It's only recently, it's interesting how long it took to get published. I don't know why. It's, I wasn't the referee. I didn't sit on it forever, but anyway, it's, it is what it is. All right. So with that little background, I will begin to say, what are some of the new frontiers? What are some interesting new directions that we might explore? I just want to make a pitch. Those of us who are academic or basic researchers at NIST, we should be thinking about new directions and new ideas. We never know how they might pan out. And so one of those is thinking about quantum computing beyond qubits, thinking about Qudits. What we mean by that is denary quantum computing beyond base 2. So, I ask myself, maybe I'll ask you the question, why should we quantum compute base 2? I mean, why do we classically compute base 2?
Base 1 won't go very far.
Exactly. Denary, and that's absolutely true. You need a tensor product structure to scale. You can't do quantum computing in a single Rydberg atom, even though you can map every computational basis state to every level. But the amount of stuff you would need, the space and energy and momentum would grow exponentially, right? Because the radius scales with the dimension of the system squared. So we can't do unary, but why binary? Well, I mean, we do it because in the end of the day, it's easiest to read out and distinguish true states versus multiple and manipulate them. I read some paper that actually in classical computing, actually the most efficient use of information would be base E. I don't really know why. I'm kind of curious. I need to understand that better, but we don't do that. But in quantum computing, I still think the answer is open. Those of you who are deeper understanding of quantum architecture to me, I mean, the thing that makes a quantum computer special from my perspective, why is a quantum computer special, is that it's both analog and digital at the same time. It's analog in the sense that we can go in between the digits through superposition, but in the end, it's robust because we can digitize errors. If we were just analog, we'd be screwed. We need a quantum error correction to make it powerful, but what's the best base to do that in? I'm not sure we know the answer to that. So I think it's worth thinking about, at least from one of the things from that perspective. So in a Qudit, we would encode quantum information, for example, base D, and have D computational basis states per subsystem. We have multiple subsystems. So some of the reasons we might think, I'm not sure these are the most important reasons why we might consider Qudits with D greater than 2 is that in principle, we can store a little bit more information. If we have n systems, we have a log, we win with the log of the base in terms of the amount of information we can store. And maybe we can think about how we construct a quantum algorithm in terms of gates, what part we offload into the entanglement between the subsystems versus the control within a particular subsystems. If the control within the subsystems is higher fidelity than the one between, perhaps that is something we might consider in terms of our compilation of quantum circuits. And in addition, and something I'm going to talk more about, I'm going to really focus this talk on, is encoding a qubit in a Qudit. So I'm going to go back after I did all this song and dance about, oh, why we should not quantum compute base 2. I'm going to go back to base 2 anyway, in the vast majority, given the time I have and what I want to share with you today. Right. So before I do that, let me just say, if we were going to do, what are some of the challenges? One of the challenges, I need to be able to do arbitrary gates on my qubits. We think about the universal gate set for qubits. We need to think about the generalization of that for qubits. So for example, the generalization of the X and Z gates for qubits is, instead of having plus or minus 1 for a qubit, I'm supposed to use this for the Zoom people, sorry. We have the Z gate now has a phase that's a root of unity, and the X gate would shift us between the different computational states mod D. Okay, so you add 1 mod D, that's the equivalent of the X and Z gates. So we want to be able to do these gates. These are not simple to do in the same way we have for qubits, where everything's in SU2 and we just exponentiate some, Rabi oscillation and we get X and Z. These are not natural unitary operations that come out of the physical thing. However, we can still think about that for the physics we have. So particularly, I'm going to think about encoding a Q decimal, a 10-level Qudit, in the nuclear spin of strontium-87. Strontium-87 has a spin 9/2 nucleus. It has 10 magnetic sublevels. And so one way, of course, we can manipulate them is with magnetic fields, with RF magnetic fields. And that generates not an arbitrary Qudit unitary. It generates a representation of SU2. It's just a Larmor procession, and that can't get me everything, but it's something. But we have more. Of course, we can manipulate these atoms optically, and we have a fairly rich spectrum of different kinds of states. We have the ground state is a singlet, because we have 2 electrons in the valence shell. They're paired in the ground state into a singlet. And then we have excited states, which can be either triplets or singlets, and they have different selection rules, and thus different lifetimes, different line widths, and we can excite them, as I mentioned, to these very highly excited Rydberg orbitals, where we can then entangle the atoms through the van der Waals or dipole-dipole type interaction. So I just want to mention, one aspect of this control that we can do. So suppose I want to make an arbitrary SU10. Okay, I want to do a 10-dimensional unitary rotation on my Qudit. How can I do that, given what I got? Okay, and one way is to use the tools of quantum optical control. Now, Bree Anderson, whom I worked with when she was in the University of Arizona, knows this very well. You can see your experiments all over again with Paul Jessen, my friend and longtime academic partner. So in particular, I'm going to talk about some work. These are a couple of papers that I've been doing in collaboration with Mike Martin at Los Alamos. He has an astronomy experiment that's ramping up. And these were the students at the time, Shiva and Anupam. So let's talk about the following idea. What I'm going to do this SUD, in particular SU10 control, through a combination of SU2 control plus something that is nonlinear in the spin components. If it's linear, the spin components, that's just Larmor precession. I need something nonlinear, okay? So the way we're going to do it is through a combination of this RF-generated Larmor precession, where I'm going to modulate some magnetic field as a function of time, together, so that causes this Larmor precession on this 10-level system, together with a nonlinear AC Stark shift or light shift. So the idea now is I'm going to shine on a laser beam that's off resonant to this triplet P1 state. Remember, the excited state here is triplet, the ground state was singlet, which means that this is a somewhat forbidden transition. It has a very narrow line width of, some, I don't know, few kilohertz, I don't know what is it, 10 kilohertz, I forget, for triplet P1. But the point is, it's very narrow compared to the very big hyperfine splitting. And remember, the nuclear spin, a little physics here, the nuclear spin is not talking to the lasers at all. If there's nothing coupling the nuclear spin to the laser, so I'm going to manipulate these nuclear spin levels. I have to do it through its proxy, the electron. And the electron is coupled to the nucleus through the hyperfine interaction. So I need to detune close enough to the hyperfine interaction, otherwise the nuclear spin says nothing. But I gotta be particularly well resolved because I don't want to hit any resonance, I don't want any spontaneous emission. So this is beautiful. Compared to cesium, which we worked on, this guy has a huge hyperfine splitting compared to the line width. So we can get massive light shifts with almost no spontaneous emission. Okay, can't resist telling that story. So, so here's the Hamiltonian, the interaction we have now. We have our magnetic interaction, which is, this RF-generated Larmor precession, where what I'm modulating is the phase of the RF. Okay, so phi as a function of t is the phase of the RF, and the IZ squared term is coming from the AC Stark shift, the so-called tensor light shift. Okay, the fact that the shift is quadratic, nonlinear, comes from the hyperfine interaction ultimately. And so if you look at this Hamiltonian, it has something that depends on Ix and something that depends on Iy. If I just had that, I can do arbitrary rotations around any axis by the algebra of SU2. But interestingly, if I just have one more term, no matter how big I is, I could be 9 halves, 25 halves, 312 halves, it doesn't matter. This makes the system controllable, meaning that this set generates the full Lie algebra of SUD, where D is 2I plus 1, no matter how big the nuclear spin is, okay, for any momentum. And so what that means to say that it's controllable is to say that there exists, given any unitary I want to produce in that set, there exists some waveform, some phase as a function of time, as long as the total time of interaction is long enough, such that the solution to the time-dependent Schrodinger equation, which is this messy thing with time-ordered exponentials, is, to whatever degree of fidelity I like, equal to the target unitary. And so the goal then is to try to optimize, use optimal control to numerically search for the time-dependent waveform that does the job. And these experiments that we've done in the past at the University of Arizona, and we're taking them now to this nuclear spin case. So just as a numeric, yes, please, question in the back. Yes.
Data space that we just tested for twice.
So that's a good question. So one of the questions you can ask yourself is, what should the ratio of beta to omega be? One of these things sets time. I can do time, say, in units of 1 over the Rabi frequency. And then the question is, so I'll set omega to 1. That's a theorist's way of saying I'm doing things in units of omega. The question is, how big should beta be? And the answer is it should be of order 1. If beta is huge compared to omega, then this thing is just a perturbation compared to that.
Slide said rotation, nonlinear rotation. And so here we're referring to the IZ squared. But if we're not restricting ourselves to talking about a two-level system and a block sphere, then I don't have very much intuition about the geometry. So are we really talking about a rotation?
Yeah, I'm using that in a very loose sense as a rotation in Hilbert space. So it's not, you know, the parameterization of the states on some manifold. There is some way I can think about the set of, I can talk about a generalized block sphere where the block vector is spanned by some basis set, for example, the Gelman matrices or the spherical tensors. And I can think about, but it's a pretty ugly geometry. And we generally only work with it algebraically and not geometrically. So when I say rotation in this case, I just mean it in the abstract space that any vector in Hilbert space is rotating, but it's not a geometric rotation in a very intuitive way, I would say. And at the end of the day, when we do the optical control, that maybe I'll show you, we don't actually, there can be geometrical Lie algebraic or Lie group based, you know, like Euler angle type constructions that try to systematically have a recipe and say, I want to do this map, this unitary. But that's not what we do. What we do is we actually say, computer, find me the solution, and you know, computer comes back. Yeah. Yeah, it's the AC Stark shift. Actually, the value of beta will depend on the ratio of the hyperfine splitting to the detuning. If I'm detuned too big, that will go down. So, but ultimately what it is just really, there's the Stark shift, and let's just say an AC Stark shift, light shift on the different magnetic sublevels that depends on the polarization of the light. And it just turns out that that is quadratic. There's a so-called tensor light shift. Yeah, it's built in. I mean, we don't, I just wanted to give you the under the hood where the physics is coming from. It doesn't really, we don't have to calculate, you know, all the atomic structure. We just say, oh, I got some Krebs-Gordon coefficients, and I got, you know, the paper I wrote with Paul, which gave us what, you know, all the, you know, appendix B in the long paper, you know, got it all. We did it once, and we just use it. Yeah.
Omega in front.
Yeah.
You have full control. How can you go any faster?
Yeah.
Setting omega.
Yeah, it does. Yes. Yeah. So what we call this quantum speed limit, I had that capital T, which was how long was my control sequence. So
Beta projects.
and the ratio of omega, if omega is 1.
So omega, suppose you can like dial omega. Then
No, but then it will be bottlenecked by beta.
right, exactly.
Yeah, but if I modulate both the amplitude and the phase, or the two quadratures, the x and y quadratures of the field, I can go somewhat faster. Yeah, but this was it just
like as a function of just beta.
There is no good analytic way to do it because of the time. If I have a time-dependent Hamiltonian, there's no easy solution to it. But it's we'll see. It's on the order of 2 pi, 2 Rabi oscillations. Yeah. Yes, this is great. I'll just do my talk with shadow puppets, and then do I get 5 minutes? No. Anyway, we'll continue the conversation with more questions. Yeah. All right. Let's see if this works. Can we hide this floor? Yeah, thank you. Good. Yay. All right. So I was going to say, just as this is one simple example. We can talk about others depending on the time. Of now, I'm not making a full unitary. I'm just making one column of that unitary. Let's say I want to make a state. Okay, so I have a fiducial state. I optically pumped into the stretch state, the m equals 9/2 state, and my goal is to make this state, which is just, I just said, hey, I want to make this superposition of these two magnetic sublevels. And I want to say, computer, find me the waveform. We have to parameterize that waveform. We don't look for functionals. We look for a discrete set. So we somehow discretize. The simplest thing to do is to just make it a piecewise constant of time. So we have a pulse, which is just a Rabi oscillation around the different axes on the Bloch sphere, in the presence of this nonlinearity, okay? And then we optimize the fidelity of the overlap between the state at the final time and the target, okay? So my target state is, this is the density matrix, the diagonal and off-diagonal elements magnitude thereof, and down here is the spin-Wigner function. Just to have another visualization, it's kind of the wave packet on the sphere. So this is a way we can think about higher dimensional systems. We think about the SU2 Wigner function. So, right, this is a spin coherent state. It's pointing along the z-axis, right? And then we want to get to this thing, which has negativity and fringes. Red is positive and blue is negative in this thing. Okay, so now let's run the movie. So as I'm going through this control sequence, this is how the wave function is evolving in time. I mean, it's swirling around, we get negativity, it's magic, and at the end of the time, ta-da! It gets to that state. So this has works quite well. We've done it in a 16-dimensional system in cesium, but now we can do it, I think, with much higher fidelity optically. Yeah.
Sharpness of.
Yeah, it's a very good question. The answer is, it depends. So, obviously, the real control waveform that I might be seeing will have some slew rates, some bandwidth, some various things. And we can put this thing through a filter that might be the true control waveform and see how much the fidelity varies. Or we can create waveforms that have those experimental constraints built in. I don't have to make this sharp. It's just an easy thing numerically to do, but one can most certainly, and one often does, create waveforms that are smoother. The experiments that were done in Paul's lab actually was done with microwaves, had these kind of, designed it this way, and the lost information in the high frequencies did very little to the fidelity in the end. But the proof will be in the pudding in the lab, and we can put that in if necessary.
Does the gradient descent get harder if you assume a Petri waveform like this, filter it, and then put it into?
Yeah, we wouldn't really do it that way. I mean, typically we would just say, well, numerically we'd say how much does it change, how important were those high, but we could parameterize from the get-go the waveforms, say, in the Fourier domain rather than the time domain, and think about the Fourier coefficients as our control parameters rather than the time domain. This is just a kind of easy way to visualize what's going on.
Can you say something about how you came up with this pulse sequence?
I didn't, the computer did.
Green. Well,
all we did is what we said was, there is a fidelity as a function of a vector of waveforms, which is my target state compared to this guy. And this is a manifold. It's your fidelity as a function of the waveform. The waveform discretized into this vector of what the phase is at these different times. it turns out there's a long series of works by Hirsch-Roberts at Princeton, which showed so shockingly how benign this landscape is. It doesn't have any traps in it. Usually doing gradient descent, you're kind of screwed because you might get stuck in a local minimum, a local optimum, or a saddle point. But it turns out if your total time is long enough and you didn't constrain with the bandwidth, this has no false maxima or false minima. It's kind of amazing. So we use that fact to just do gradient descent. And there's an algorithm called GRAPE, which stands for gradient descent something or other, pulse engineering, which gives us a recipe for calculating the gradient of this easily so that you don't have to use Nelder-Mead or anything inside the computer. The gradient is calculated, just put it on MATLAB or Python or whatever, or you ask ChatGPT to write it for you, and it does it. All right, continuing on. So what I want to spend my remaining X minutes doing is talking about slightly different part of this Qudit control, which I mentioned, which is encoding a qubit in a Qudit. Okay, this is work done in collaboration with my colleague Milad Marvian. He's really the lead theorist on this, and he's a quantum error correction expert, and my students Shiva and Vikas. Oh boy, this actually is in. God, I need to update the stamp slide. It's been published. All right, so. So, you know, we mentioned, quantum error correction, fault tolerance, that's a big challenge today. And, you know, what are the key ingredients to doing quantum error correction? We want some kind of space to have redundancy, and so the information isn't destroyed when there are errors. So we need a big enough Hilbert space to encode that redundancy. And then we need this ability to do what I think is really just what I call a quantum eraser. So you guys, who's ever heard of the quantum eraser experiment? I'm curious, like what is in, yes, not everybody. I mean, it is an important idea in quantum measurement theory that in principle, we lose coherence because the environment has which way information about which path or which state the system is in. And if we can somehow erase that information, then we can recover the coherence. That's what quantum error correction does when you are measuring syndromes and doing the correction based on the syndrome. You're basically doing quantum eraser. Okay, so there are various approaches that one can take. One can think about encoding a logical qubit in many, many physical qubits. The surface code, color code, so forth are like that. But we can also think about pieces of this that involve not using multiple qubits to store that redundant entry, but to the degree to which we can use the other sublevels within a qubit as a way of partially perhaps saving ourselves some physical systems and control and so forth. And that's kind of behind the schemes that are being done in bosonic quantum computing platforms. The so-called GKP states or cat codes are basically doing that. And, you know, the challenge to make this is, you know, we got to get beyond break even. We got to reduce errors faster than we're creating them when we're trying to do error correction. That's what the threshold theorem is about. And we have to think about how much resources we have, how many auxiliary systems, what the control schemes are to do that. But I think what we're coming to understand more and more is that co-design should probably be a very important part of how one is designing the quantum error correcting code. So one should really think about what are the base physical errors on the system? How do we deal with those first and then get to a more abstract, higher level for doing quantum error correction? So the inspiration we're taking is sort of a combination of the Shor code, which I'll remind you a little bit about, and the so-called cat codes, which were first proposed in this paper by Shruti Puri and et al. Now over 5 years ago, where the idea was to encode a qubit in a superposition of coherent states of a bosonic mode. So I have a coherent state which has some mean number of photons, my logical 0, and then the state that's on the other side of phase space is my logical 1. And in that case, flipping from 0 to 1 and 1 to 0 is basically forbidden, because I can't go from the coherent state of all these photons to the coherent state that has all those photons. So in that case, my code is one where bit flips are highly suppressed, and I just have to deal to some degree with phase flips. Okay, and that I could be done with a simple repetition code. So let me back up and explain what I'm saying here. Let's just remind ourselves of some of the basics for those who are not completely steeped in this stuff. So when we think about error correcting codes, the basics are to think, okay, if I have bit flips, those are so-called X errors. They take 0 to 1 and 1 to 0. And I can protect from bit flips through a simple majority vote by having logical qubits redundantly encoded, for example, in a repetition code, okay? In quantum mechanics, of course, there are other kinds of errors. There are so-called Z errors, which are phase flip errors, which takes the plus state to the minus state and the minus state to the plus state. That's the superposition of 0 and 1. The plus and minus equals superposition of 0 and 1s. And if all I had were phase errors and no bit flip errors, well, then I can also have a classical error correcting code, which just was a repetition of those states. The problem with quantum computers is that we got both. We have both X errors and Z errors. And, you know, in the complete strike of genius that Peter Shor had, in many strikes of genius, say, well, we can do both by just kind of concatenating these. So this was the Shor code, where I have an inner layer, which is correcting the bit flips. And then I have, so I'm going to use, so logical 1 there is 1, 1, 1, and logical 0 is 0, 0. So that's a GHZ state. And then I have 3 copies. This is a 9-qubit error. Shor called these logical 0 and logical 1, but I think he should have called them logical plus and logical minus, because that's just looks just like the phase code. It's the same thing. It's just a label of what you're calling the X basis or the Z basis at the logical error. So this was the first quantum error correcting code, and we're taking inspiration from that. But before we do that, I want to say the goal here is to create a system, or have a system where we have a very biased set of errors. Let's say the Z errors completely dominate over the X errors. In that case, we can try to first beat down the dominant error to the level of the thing that is barely error at all. And then I can create another layer of quantum error correction on top of that, where it might be the case that I've reached better the threshold for fault tolerance because of this bias, right? If there's a tiny error that is, if I can beat down the big error to the level of the tiny error, well, then I can try to get to a place where that qubit will have a better threshold for a standard code, like a CSS code, surface code, etc. So that's the goal, a biased qubit. That's what the cat qubit was. but we're going to have spin cats, okay? So here's my qudit again, which is really a big spin, okay? And in our case, J was, or I was 9/2. And we're going to encode a qubit where 1 is one stretch state and 0 is the other stretch state, okay? And what you can see in this case, it's extremely unlikely to flip from 0 to 1. There's no physical process that will easily flip me from 0 to 1 or 1 to 0. And so we kind of can divide the say, if we say everything in here I'm going to call my 1 space, and everything in here is going to be called my 0 space. If my errors that occur in this atom keep me, if I start here in the purple, and if I start here in the blue, and I can push it back, then that's a correctable error. If I cross the Rubicon, if I get from one side to the other, I'm screwed. I can't tell whether it came from 0 or 1. But because I have all this space in between, I can keep the bit flips from happening. The phase flips happen. The phase flips are Zeeman shifts. We'll come back to those in a moment. But the bit flips are incredibly unlikely if this is a big enough spin. So where our Z is a stretch state, or 1 is the other stretch state, and our so-called plus and minus states are what we call spin cats, okay? I don't put the hyphen anywhere because I'll annoy Alexei. All right, so, and then the idea is in the same way that was considered and explored for the bosonic case, then the only remaining error, if we can somehow get rid of the bit flip errors and keep them from happening, push those purple and blue things back to the edges, are just phase flip errors. And we can correct those with a repetition code and then do something else on top of that if we need to. Okay, that's the idea. So what are the physical errors in the system? The physical errors are, we could have some stray magnetic fields which cause Larmor precession rotations. Sorry, I'm calling it J rather than I now because it's generic angular momentum. It doesn't have to be a nuclear spin. And if this is a small error, then I could just say, what does this do? What does this rotation do to the logical states? So this will cause, if I have a rotation along the z-axis, which is equivalent to a Zeeman shift, that is a phase flip error. Okay, that flips plus to minus and minus to plus if it's small. If I have an X error, what an X error does is the X error involves raising and lowering operators on their ladder operators. So that will take the things that are on the outer edge, the cat states, to what we call the kitten state. So the kitten state is just, we have littler and smaller kittens, which are superpositions of m equals something and minus m, some layers in. So a JX error will take a cat state to a kitten state. That's a kind of amplitude damping error. But it's not a bit flip error, right? Because I didn't go all the way to the stretch state. And I got to bring the kittens back to the cats. If I can do that in a way fault tolerantly, I win. Okay? So keep that in mind. This is what I mean when I put the little sub label here. K tells me how many layers I've jumped in. Plus sub 1 is 1 layer in. Okay. All right. So notice there is a bias here, right? I mean, if J is big enough, this happens with, the phase errors are going to be bigger than the damping errors. And so I should be able to correct this amplitude damping without affecting that. Yeah.
Why are the Qudit states symmetrical?
They're not. This is a subspace. I'm defining, and we'll come to this at the very end as an example. As you say, I'm going to jump into maybe one of these states or the other, but it is in the subspace that is spanned by those. And at the end of the day, I got to do a quantum erasure to get back that coherence. So we'll see how that works. So I'm just defining this as a basis, but not the state into which it jumps. All right. So optical pumping, for example, if I absorb photons and emit photons, that's a kind of amplitude damping channel here. And so if I can push things back in a way, correct those errors, erase the information about what happened and bring it back to the cat state, then I have kept the amplitude damping from happening. Okay? Okay. Now, given the time, I probably won't go through all these details. But I just, for some of the experts here, the point here is that when we think about errors, when we have a set of qubits, we usually think about the errors as associated with local Paulis acting on, I have an X error or a Z error, or it happens on more than one, and my errors are related to the Krauss operators are related to products of Paulis. There are Pauli errors. Here, I don't have a bunch of qubits. I have one qudit, which is really a spin. And so the natural basis of operators in which I should think about them are the polynomials in the spin components, which are the spherical harmonics or the so-called spherical tensors. Those are the basis of operators. And we're going to restrict ourselves to errors that are either first order or second order because those are the things that correspond to small rotations and optical pumping. They could take me 1 or 2 M's in, okay? Those are the set of errors we'll restrict ourselves to. And so these spherical tensors, what I don't want the operations I do to create uncorrectable errors. And so that operations have to not take me to higher order polynomials. They have to take linear polynomials to linear polynomials. And that means the only operations I want to do are SU2 type operations, even though I talked about SU10. In the end, I'm going to try to restrict myself to SU2 because they will maintain this error structure. Not necessarily. I mean, ultimately, in the operations I do, that are not going to create errors, I am absolutely going to set beta equal to 0. But sometimes, I don't know where the question came from. Oh, yes, excuse me. So in this case, absolutely, there's no beta. We can talk about it afterwards, the cases where I'm going to use that quantum optical control for some features. But when I do gates, I only want to do linear rotations because otherwise the gates are going to take correctable errors to uncorrectable errors. It's going to change the rank of my spherical tensors. So for example, if I do a 180-degree rotation around the x-axis or y-axis, that takes this state to this state, but it doesn't mix. All the kittens are separately dealt with, okay? Every kitten subspace does the same thing. All right, so what are the gates we're going to use? Remember, these are qubits. We're encoding a qubit in a qudit. The gates we need single qubit operations. We need X, Y, and Z. X, Y, and Z are really 180-degree rotations around the X, Y, or Z axis. So we could just generalize them to spins. So this is my X, Y, and Z. They're not poly X, poly Y, or poly Z anymore, but they are the objects that flip the spin and fit the phase appropriately. Okay. Now, that's not enough for single qubit universal gates. I also need, for example, Hadamard, right, which takes me to superposition. For a spin 1/2, that's a rotation on the Bloch sphere generated by the Pauli, which is an SU2. But for my bigger spin, that there is no way to go from the stretch state to the spin cat state by a rotation, by an SU2 rotation. So that is not a good gate anymore. I can't use Hadamard. So I've got to do universal quantum computing somehow without having Hadamard, because I can't do this. I could do it through optimal control and beta and all that stuff I just showed, but that's not a good way. I'll make uncorrectable errors. So we have to make use of a different gate set, and this was studied now years ago, holy moly, by John Preskill and Alafaris, where they looked at these kinds of biased qubits and came up with a different gate set. It has preparation of different states and then measurement in different basis, but importantly, a C-naught. Okay, I can't have CZZ and Hadamard because I ain't got no Hadamard. So I got to have a C-naught, and I've got to have a C-naught that is bias preserving. Okay, one that only does the SU2s. Now we don't have time. Things fell apart, but I'll just say with that we can do it. We have this bias preserving C-naught, and we do it. And I can answer this more at the end of the question time. But the point is, with our Rydberg blockade, what we want to do, we want to apply the X gate to the target qubit only when the control is in 1. If the control is in 0, we do nothing. That's the controlled knot. And we can do that through a sequence of pulses with the Rydberg blockade, which I don't have time to explain. So I'm going to just say, believe me and ask me more. But the bottom line of it is that through a series of using beta and optimal control, I can put the target atom into the Rydberg only if the control is in 0. And if the control is in 1, I put the target in an intermediate state that has a different G factor. And because of that different G factor, the Zeeman splitting is different. And what that means is I can use RF control to do a 360-degree rotation on this atom, while simultaneously I do a 180-degree rotation on that atom. So I've done the controlled X. I've rotated the target only when the control was in the right state. And we can do that in a way that only involves rotations. Okay, that's the bottom line of it. It looks like that. All right, I'm going to then just say how we then can do this error correction. Okay, and how much time should I take, Steve? I should finish in 0? I should finish. I'll finish in just a couple of minutes. I just want to say this one thing. So let's say an error happened. If an error happened, the atom, this amplitude damping, let's look at in one of these subspace, the information that was in the stretch states is now mapped to this kitten state. And I want to put it back to the cat state. I can do that correction autonomously. I don't need to do a measurement syndrome and correction. I just have to swap out the entropy. I don't know which of these kitten states sits in. K is unknown. And I want to put it back into the cat state no matter what K I'm in by doing a series of controlled knots with an ancillary cat state that I prepare with beta. So I can make a cat state with beta, and I can make a very good cat state with optimal control, do the controlled knot. All of a sudden, I've swapped the information onto the clean ancilla, which has no entropy, and all the entropy is thrown into the other side. Error correction is a dumping of entropy. It doesn't require measurement. It just requires very pure ancillas, and then you can dump the entropy out and have that. So that's an important agreement. I'm going to skip all this and go to the last bit, which is this answer, because I think this is, oops, I'm going to go the other way. Yeah. Okay, so let's see how this works. This comes to your question. Let's say I had this quantum information in this qubit, okay? And I then say, oh no, an error happened. Here's an error. I optically pumped, I absorbed a photon and I spontaneously emitted, and now I'm in this particular state, 1. So the plus state got sent to that state, which is a superposition of those two cats. And the minus state also got sent to that state, but with a different phase. Okay, so the state that I had up here is now, after this error happened, the first qubit is in this state, which is a superposition of the plus and minus states of the kitten state with a minus sign. Okay, so now through the repetition code, I can get rid of that. I've removed that error through majority voting, so that everything here, I keep all the states that have the same plus state, but I got this. And so by just bringing in 3 fresh ancillas, I can swap out that entropy and recover. So I would love to see this experiment done. This is a way that we could correct optical pumping with 3 atoms. Now, that's not quite true. I need all these ancillas. I got to do a ton of quantum control. It's not going to be easy. But I just think it's fascinating to think that we can erase this which way information about where things went. Okay, I will conclude there. Here are some references, and I thank you very much for your attention. Sorry to... Yes, Nicole.
Motivations for doing quantum computing with qudits is that it's possible that when you shift to using qudits, then instead of just performing a whole bunch of entangling operations, you can perform fewer entangling operations plus some kind of compensating control on single qudits. And maybe it's possible that the control on single qudits could be easier than this extra entangling control. Have you found that to be the case in an example?
Yeah, the answer is I haven't done it.
Ivan,
I haven't worked out the details on this. So this is something that it's really more musings at the moment than rock solid results. There have been some works of people looking at different compilations of circuits that sort of trade off how much of the entangling gates we do within some qudits. But there's some hard work to done, and I haven't done it. So I really can only say that, yeah. Yes.
On head code, there is possible to construct like a for-like head code, so you can correct both activating and photon loss here. Correspondingly, do you think it's possible, like with cat, you can consider corresponding like for-like cat, so you can automatically like correct empty damping and also can correct like the optical pumping without using repetition here.
Yeah, I'm not familiar with that, so I can't speak to it in detail, but I would say pretty much anything that can be done in the bosonic world can be done in this as well. I can think about, cats along different axes, right, which would correspond to, the kind of multiple cat directions that one would have in a bosonic system. But I haven't studied that myself, so I can't really speak to it. But I would be optimistic. I think anything that is done in the bosonic sense could be also done with the Qudits as well.
Okay, well, since we're running a little late, why don't we thank Ivan again?